Hi guys, welcome back to the channel. In this lecture, we are going to discuss one problem in which we will be analyzing one continuous beam and we will be finding the what will be the collapse load for this structure, right? So here we are given this continuous beam ABC, which is loaded. The AB portion is loaded with the point load and which is acting at the center, and this portion BC portion is loaded by a UDL. Okay. And the magnitude of this UDL is given W by 6 kilonewton per meter, right? So in this problem, we need to find what will be the load required for the first plastic hinge and what will be the total load required for the collapse, right? So basically, this is an indeterminate structure. Static indeterminacy is basically 1. Okay. So if you want to find what will be the load required for the plastic hinge for the first plastic hinge formation, we need to follow the incremental load method. Incremental load method. Okay. So we have already discussed this thing, right? So for that, now we will be using this incremental load method. For the first plastic hinge will be formed where the bending moment will be maximum. Okay. So basically, this is an indeterminate structure. Okay. We need to analyze this structure to find the critical position of the bending moment, or you can say that at the point where the bending moment will be maximum. Okay, so first step is to analyze this structure. Okay, so basically this is an indeterminate structure, so it is little bit tough to solve this what you can say that to solve this structure, right? So how we will be analyzing the structure? We will be using the unit load concept, over here. Okay, and we will be using the compatibility equation, right? So you can see that we will be using the unit load concept. Okay, first we need to find what will be what redundant we will be taking, which reaction we will be taking as a redundant. Okay, so here I am taking RC as redundant. Okay, so if you are taking RC as a redundant, our structure will look like this. Okay, now this distance is 4, this is 4, and this is 12, right? Plus we will be applying unit load at the end where we have taken the redundant. Okay, so this is basically total 8 meter. This is 12 meter, right? So we have taken the RC as a redundant, and in place of redundant, we are applying the unit load. Okay. Now we will be using the compatibility equation, and compatibility equation will be total deflection at this point C will be 0. So delta C will be 0. Okay. So delta C we can write delta L due to load plus del 11 into RC equals to 0. Okay, deflection at this point due to dead load, which is delta L, and plus deflection at this point due to unit load multiply by RC will give me the total deflection due to this redundant RC, right? So we will be using this condition. Okay, this we have already discussed in previous lectures, right? So delta L we will be calculating using this formula. Okay, and del 11 we will be calculating using this formula. This we have also already discussed in detail, right? You can refer my previous lectures. Okay, these things are already discussed in details over there, right? So we will be using these two formulas to calculate the deflection due to dead load, okay, due to this load, and del 11 is a deflection due to this unit load which is acting at this point C. Okay, so now we'll be forming one table. So this is A, this is B, this is C, this is D, this is A, this is B, this is C, this is D, right? So now let us calculate. This is M, this is M. Okay. So and this M, and I'm assuming this W, I'm taking this W as 1 kilonewton. Okay. So this I'm taking as 1 kilonewton. This will be 1 by 6 kilonewton meter per meter. Okay. So for the CD portion, the moment will be 1 by 6 into x by 2, right? At a distance x, the moment will be 1 by 6 into x total load into x by 2 will be moment at a distance this x section, right? Due to this and the direction, and it will be negative. Why negative? Because it is causing hogging. Okay. Due to this unit load, for calculating M value, the moment will be 1 into x. Okay, I can write this as x square over 12. There should be no doubt in this. Okay. Now for AB portion, EI value is constant. Okay, remember it is constant. It is given in the question. Okay, and for the AB portion, we need to analyze first this part, and we need to analyze then this part, right? So if you analyze this thing, you take moment about A point. So I can write 1 into 4, okay, minus RC. Sorry, this is ABC. Okay, so this is nothing but this is our, oh sorry, this is ABCD. This is RD. Sorry, this will be RD. Okay, so RC into 8 plus 1 by 6 into 12, right? And this into 8 plus 6, this is 14. Okay, so this should be equals to 0. We need to find the moment due to this load. So first we need to analyze this. We need to find this RA reaction. Okay, so the value comes out to be 4 plus 12 into 14 divided by 6, 32. So RC comes out to be 34 kilonewton. Okay, so if RC is 4 kilonewton, I can write RA plus RC equals to how much it is? 1 plus 1 by 6 into 12. Okay, so this is RA plus RC is equals to RA plus RC equals to 3. So RA will be here minus 1. So the value of this RA at this point is minus 1. It is acting downward. So this negative sign is showing that this force is acting downwards. Okay. So now the moment for AB will be 1 into x. Again, it is causing hogging, so that's why it is negative. Now, if you analyze this portion, so again we are taking moment about this point. So I am writing 1 into 20 plus RC into 8 equals to 0, right? So from here, RC is minus 20 divided by 8. So it is minus 2.5, right? So we have one equation. So this at this point, the reaction acting is 2.5, right? Here we are applying this unit load 1 kilonewton. Okay, so at this point the reaction will be 1.5. Okay. So from here, if you calculate the moment at a distance x, it will be 1.5 into x, right? So now let's come to this BC portion. Okay. So for the BC portion, I can write minus 1 into x plus 4. Okay. And minus this is 1 into x. Okay. And I am taking x from this, from B. Alright. Again, for this portion, it will be 1.5 into x plus 4. Okay. So this will be minus 2x minus 4. Okay. And the integration will be, here the integration will be 0 to 12. Here it will be 0 to 4. Again, here it will be 0 to 4. Okay. So what we did over here, we find these values, m small m. Okay. Now we will be calculating this delta n and this del 1, and we'll putting those value in the compatibility equation to find the redundant reaction at this point D. Okay. Right. So now first calculate what will be delta L. So delta L will be 0 to 12 minus x square over में 12 into x into dx over में EI plus 0 to 4 minus x into 1.5 x over में EI into dx, right, plus integration 0 to 4 minus 2x minus 4 into 1.5 x plus 4, right, and again this is over में EI. Okay. So if you solve this integration, it will be, first value will be okay guys, so we'll be calculating this integration value. So first term is 0, 12, this is minus for x square divided by 12, this is actually x cube divided by 12. So this value comes out to be this value minus 432 plus, now we are calculating this value. So again 0 to 4 minus alpha x into 1.5 alpha into x. So this value is minus 32 and plus, now we are calculating this the integration value of this integration. So again it will be 0 to 4 minus 2 x minus 4 into 1.5 alpha x plus 4. And this value of this integration is minus 304. Okay, so total value will be minus 32 minus 432. So this is 768. Okay, so this is the value of delta L, 768 over my EI. Okay, so this thing is done. Now we will be calculating what will be the value of this del 11. So it will be 0 to 12 x square into dx plus 0 to 4 1.5 x over my square dx over my EI, right, and plus 0 to 4 1.5 x plus 4 square dx over my EI, right. So if you calculate the value of integration for this part, it will comes out to be so this is 576 plus 0 to 4 1.5 square. This is 48 plus 1.5 into x plus 4. So this is 336. Okay, so total value will be 336 plus 48 plus 576. So this is 960 over my EI, right. So if you put these two values into this compatibility equation, we will be getting the value of the redundant RD, right. So equation will be 768 over my EI plus del 11 is 960 over my EI into my RD equals to 0. Okay, so this thing will cancel out each other. So 768 divided by 960 will give me the value RD equals to 0.8, right. So the value of the redundant at this point is basically 0.8. Now it will be very easy to locate the position of the maximum bending moment. We found the redundant. Now we will draw the bending moment diagram for this continuous beam. Okay, so this is the important part in this problem to analyze this structure. Okay, you will, if someone asks you what is the total collapse, then you don't need to do all this, right. But we are interested in how the plastic hinges are forming, at what load the first plastic hinge is formed. So for that you need to follow this incremental load method you need to analyze this continuous beam. Okay, so now we'll draw the bending moment distribution diagram. So guys, we will be drawing the bending moment distribution for this continuous beam. Okay, at this point we know the reaction is 0.8. Okay, so this reaction is 0.8, and I'm assuming that W is 1 kilonewton. Okay, why we are using this we'll see later, right. So now let us first calculate what are the reactions generated at this A and at this C point. Okay, so first take moment about A, summation MA equals to 0. Okay, so I can write 0.8 into 20 plus 1 by 6 into 12 into 6 plus 8. Okay, so this will be minus, and again this is 1 into 4, and plus RC into 8 will be equals to 0, right? So if you solve this equation, so this is minus 2 into 14 minus 4, 16. So RC comes out to be 2 kilonewton. Okay. Now RA plus RC plus RD is equals to 1 plus 2. Okay, through vertical equilibrium, summation F5 0. RC we know 2, RD is 0.8 and this is 3. So this will be 3 minus 2.8. So RA comes out to be 0.2, right? Now we know all the reactions. Now we'll draw the bending moment diagram, right? So from the bending moment diagram will be straight line up to this point, and the value of the moment will be 0.2 into 4. So this is 0.8, right? So what will be the bending moment value at point C? So I can write RA 0.2 into 0.2 into 8 minus 1 into 4 minus 1 into 4. Okay, and I'm assuming that bending moment at MB is acting like this. Okay, so this will be 0. So the value will be 0.8 into 8, 0.2 into 8 minus 1 into 4. So MB comes out to be 2.4. Okay, so if you draw the bending moment diagram, the MB comes out to be 2.4. This is creating hogging, so it will go like this at this point. So this is 2.4. Okay, and for this UDL case, the bending moment will be like this, right? And the maximum value of the bending moment will at this point will occur at where the shear force will be 0. Okay, so if you calculate the shear force from this side, I can write 0.8 plus 1 by 6 into x will be equals to 0. So x here will be 0.8 into 6, which is 4.8. So at this point, we are getting the maximum value of bending moment. And what is the maximum value of bending moment? This we can calculate. 0.8 into 4.8 minus 1 by 6 into 4.8 into 2.4. Okay, so this value comes out to be minus 4.8 into 2.4 divided by 6. So this value comes out to be 1.92. Okay, now you can see that at the critical position where the maximum bending moment will occur, we find this value, these values. Okay, 0.8, 2.4 and 1.2. Now you can clearly say that the first plastic hinge will form at C. First plastic hinge will form at C point. Okay, there should be no doubt in this, because the bending moment is coming maximum at this C point, right? Out of these three critical points, bending moment is coming at the maximum at this C point. That's why first plastic hinge will form at this C point, and we are not bothered about any direction. Okay, so we are just considering the magnitude value, right? So first plastic hinge is forming at, you can say that at this point, this C point. Okay, and how much load is required? Now we will be using the interpolation, because our analysis is linear elastic, right? So if we are in this linear state, our analysis is elastic plastic. So we are in this is elastic state where the load and deformations are linear. Okay, so So for these 1 kilonewton, the moment generated at C point is 2.4. Okay, and I forgot to mention that maximum MP value is 120 kilonewton meter. Okay, this is the plastic moment for this section, and this beam is prismatic, so this MP value will be constant throughout this beam. Okay, so due to this 1 kilonewton load, the moment generating at this C point is 2.4. So how much load will be required to generate a moment of 120 kilonewton meter? Because this is the plastic moment. Okay, so it will be 120 divided by 2.4. Yes, so X equals to 50 kilonewton, right? So when W is equals to 50 kilonewton, first plastic hinge will form. First plastic hinge will form. Where? At C, right? So this is the case. Now let us draw the loading for the first plastic hinge. So if this is the beam, right? So here, this is the load, 50 kilonewton load will act at this point, right? And this, you divide the magnitude of this UDL will be 50 divided by 6. So this value is 8.33. 50 divided by 6. 8.33 kilonewton per meter. Okay. For this case, when the loading on the beam is look like this, then the plastic hinge will form at this point. This is the first plastic hinge, right? For this loading case, for this loading condition, if your magnitude of this UDL is 8.33 kilonewton meter, and the point load acting at this AC portion is the point load is acting 50 kilonewton for this AC portion, then you can say that the plastic hinge will form at point C. Okay, but remember that this is not the collapse of the structure. Okay, we need to have two plastic hinges for the complete collapse of the structure, right? Because static indeterminacy is 1, right? So we need one more plastic hinge, one more hinge to make the structure collapse. Okay. So now our second condition, and this is the most important and beautiful part of this problem, where will be the second plastic hinge will form. Now you can say that by looking at this diagram, the plastic hinges from the next plastic hinge will form definitely at point C, definitely at this point. Let us denote this point at E. Okay, by looking at this bending moment diagram. Okay, now look one thing. This is the case here at this C point. The plastic hinges, there is formation of the plastic hinge. Okay, and this is the end portion. Now if you apply the load after the formation of the first plastic hinge, the bending moment diagram, this portion cannot provide any extra bending moment. Okay, so I am taking this as an internal hinge, right? So this thing, when you are applying a UDL, let us suppose again 1/6 kilonewton meter, and here this 1 kilonewton load is acting. After the formation of the first plastic hinge, this bending moment will be maximum at the center, and which is at a distance of 6 meter. Okay, after the formation of the first plastic hinge, before the formation of the up to this condition, the bending moment is coming maximum at this point. Okay, at a distance 4.8. Now when you are applying load after the formation of the first plastic hinge and first plastic hinge, the bending moment will come maximum at the center. Okay, so your critical position will always lie between 4.2 to 6 meter. Okay, this thing will always hold. Okay, your critical position will always lie between these 2 points, right? 4.8 and 6. Why this is happening, we have discussed. Okay, so now we know one formula. We will derive this thing later. Okay, if you are having one cantilever beam, propped cantilever beam, right, and it is loaded by a UDL. Okay, so the first plastic hinge will form at this point due to this moment at A, and the second plastic hinge will form at this point, which is at a distance of 0.586 L. Okay, if this distance is L. Okay, so here also the similar thing is happening. You can relate this case to this case. Okay, initially this is a type of a propped cantilever beam because the moment is coming, because this portion is providing moment. After this has reached to yield state, this cannot provide any moment. Okay, so the second plastic hinge will form at a distance of 0.586 L. Okay, and this result we will be using in our problem. Okay, and derivation of this we will see later when we will be discussing the static method. Okay, so next plastic hinge will form at a distance 0.586 L from C point. Okay, so and what will be the value? 0.586 into L. L is what? L is nothing but L is 12 meter. So this value will be 0.586 into 12. 7.032. Okay, so this is the case. After the formation of the first plastic hinge, again you are applying a load 1/6 kilonewton meter, right? So we have now we have discussed that the plastic hinge will form at a distance of 7.032 from this C point. Okay, now we will be calculating what will be the moment generated. What will be the moment generated when this is our loading conditions. The magnitude of this UDL is 1/6 and the unit load is 1 kilonewton, right? So we will be calculating what will be the moment generating due to this loading, and then we'll apply the linear interpolation to calculate the actual collapse load value. Okay, now right. Okay, so we will be analyzing this thing now. The moment generated at this point, and this is 12 minus 7.032, 4.968 meter distance. What will be the moment value? Okay, this thing we need to calculate, right? So this portion I am treating as internal hinge. Why internal hinge? Why this hinge is given? Because this cannot provide extra moment. This portion has already yielded. Okay, so here this load is acting 1/6, and here this is 1 kilonewton load. Okay, so if you calculate, I can write, this is R, this is D. I can write RD into 12 minus RD into 12 minus 1/6 into 12 into 6 equals to 0. Moment at this C will be 0. Okay, because it cannot provide any extra moment, right? So RD into 12 is equals to 12. So RD will be 1 kilonewton. Okay, so RD will be 1 kilonewton. Right, now moment at a distance 4.96 meter will be 1 into 4.968 minus 1/6 into 4.968 into 4.968 divided by 2. So this will be the value of M. Okay, so the value will be 4.968 minus 4.968 into 4.968 divided by 12. So the M value comes out to be 2.911248. Okay, now again we will be using the linear interpolation. Due to 1 kilonewton load, the moment generated at this point will be is 2.911248. Okay, this thing is done. Now the important part is, you see here, due to this load, this much moment is generated at this point, right? This at a distance 4.968 meter. Okay, when the first plastic hinge was formed, how much moment is coming at this point? How much moment is coming at this point? That thing we need to calculate, because some portion of this MP, the plastic moment, is already covered in this analysis. Okay, when the first plastic hinge is formed at C, at this point, this is 4.968. There is already some moment. Okay, so you cannot do that. How much moment is required for 120 kilonewton? This is not the correct way, right? You need to find a difference. Basically. So when the first plastic hinge was formed, the moment generated at this 4.698 the moment generated at this point was basically, this load is 0.38 into 4.968 minus 1 by 6 into 4.968 square divided by 2, right? So this value will be into 4.968 minus 4.968 square divided by 12. So the value comes out to be 1.917. Okay, this is the moment when there is first formation of the plastic hinge. Okay, and this is due to unit load. So due to 50 kilonewton load, it will be 50 into 1.9117, and this value will be 50 into 1.917. This value comes out to be 95.85 kilonewton meter. Okay, so the extra moment which this beam can take will be 120 minus of 95.85 after the formation of the first plastic hinge. So if you subtract this thing, so this value is 24.15. Okay, now this portion where the second plastic hinge will form can take extra moment of 24.15 kilonewton meter. Okay, so due to this load, due to 1 kilonewton load, now we will be using linear interpolation for this thing. Due to 1 kilonewton load, the moment generated was 1.248, and for 24.15, how much load is required? This will be 24.15 divided by 2.911248. So this value is x equals to 8.29 kilonewton. Okay, so the extra load after the formation of the plastic hinge, after the formation of the first plastic hinge, the extra load which it can take is 8.29. Okay, and total collapse will be 8.29 plus 50, and this is 58.29 kilonewton, right? So this is the total collapse load for this beam will be 58.29 kilonewton meter. Okay, We will be drawing this load on the beam where the collapse will, when the collapse will happen. The loading condition will look like this. So this is 58.29, and here this magnitude of this UDL will be 58.29 divided by 6. So when you are applying this loading condition, the plastic hinge will form at this point and at this point. So there will be the collapse, right? So this is the collapse. This is the collapse. Okay, this is during collapse. Okay. Okay, guys. So now you can see that the importance of the bending moment diagram, bending moment distribution. Okay, this is the very important point, that the second plastic hinge will not form at this point. It will form at a distance little more than this 4.8. Okay, why this thing happened we have discussed. Okay, so this is the important thing to remember in case of the UDL. Okay, if there had been a point load over here, then there was no problem. Then there is no problem. Okay, the maximum moment will always be there under the point load. Okay, guys. So this is the case. Now, if you show the moment, how the moment is acting, so it will look like this. At this portion, this is anti-clockwise, so here it is clockwise, MP. This is anti-clockwise, MP. Again MP. Again MP. Okay. So this is the basically how the plastic moment will act. Okay. This is always opposite to the rotation, right? Remember that thing. Here the rotation, the direction of the rotation is like this. So to oppose that, the bending moment will act opposite to this direction. Okay. So this is the way you draw the bending distribution. Okay, and the bending moment at the collapse, bending moment diagram at the collapse will look like this. Okay, first there is MP moment. If you want to draw the bending moment at the collapse, you can solve this equation, right? There is no issue. You can solve this equation. You know already MP values. MP is 120 kilonewton meter, and you can solve this thing. Okay. The easy way to do now, next way is to take, let us suppose, take B as a redundant. Okay. Take B as a redundant. When you are taking B as a redundant, there will be internal hinge at this point. Okay. So due to this redundant, the moment will look like this. I'm drawing the moment due to redundant only. Okay. And due to this load, the moment diagram will look like this. Here this will be MP, here this is MP. Okay, so your bending moment diagram will look like this. Okay, so how we draw this thing? Let us suppose you are releasing this moment MP value. Okay, you are taking MP as a redundant. Okay, when you are taking MP as a redundant, so the beam is divided into two parts. And you are taking MC as redundant. Okay. Now due to these redundants, the bending moment diagram will look like this actually. Okay, if you are taking this as a redundant, you are solving these two equations. You are applying moment like this, okay, and here also you are applying moment like this. So if you draw the bending moment diagram due to redundant, it will look like this, okay? And due to load, that you can draw, that is free bending moment diagram, right? So if you draw this thing, if you overlap these two things, the bending moment diagram will look like this, okay? So now you can check the yield condition also anywhere in the beam. You can say that anywhere in the beam, the yield condition will always be satisfied, equilibrium condition will be always be satisfied, right? So you can do, if you want to solve the equilibrium equation, you can solve any portion of this beam, right? First you need to calculate the reactions and you check the equilibrium equation, whether it is true or not, whether the equilibrium equation is satisfied or not, okay? So guys, if you have any doubt in this problem, you can write in the comment section, okay? So all the three conditions are basically satisfied: equilibrium, yield condition, and what you can say that mechanism. Mechanism is how, because two plastic hinges are formed, okay? And for the equilibrium equation, let us discuss about that also. For the equilibrium condition, first you calculate the reactions due to these two forces, okay? First you calculate the reactions, right? Okay. So now let us check the equilibrium condition for this. This is 58.29. This is 58.29. Okay. So this is 58.29 by 6. Okay. So now this distance is basically 4. How much was the distance? 4.968 something. Okay. So first you calculate the moment. You take this beam, okay? You take this beam, here the moment is acting 120 kilonewton meter, okay? And there is a UDL 58.29 by 6. There will be one reaction which is RD, okay? So if you calculate, if you find this RD value, RD into 12 plus 120 minus 58.29 by 6 into 12 into 6. So this will be 0 basically. For summation m equals to 0. So this value will be 120 minus 58.29 into 12 divided by 12. So RD comes out to be 48.29. Okay. So if you calculate moment at this point, this 4.968, for the equilibrium to satisfy, that moment should be equals to MP value. Okay. So 48.29 into 4.968 minus of 58.29 by 6 into 4.968 square divided by 2. This will become how much this value? It should come out to be 120. If it is not, then equilibrium condition is not satisfied. So 48.29 into 4.968 minus 58.29 into 4.968 square divided by 12. So this value is coming out to be 120. Okay. So equilibrium condition is also satisfied. We have calculated this value. At this moment value at this point. So it is coming out to be 120. So equilibrium condition is also satisfied. Okay, so how you satisfied that equilibrium condition? You calculated the moment at this point, and it is coming equal to it is coming equal to the plastic hinge moment, which is 120. So this structure is basically is under equilibrium, right? So guys, I think I have covered this problem in detail. Still you have any doubt regarding this, you can write in the comment section. Okay guys, so thank you very much. Now we will be meeting in next lecture. Okay.